On the evening of January 3, 1961, at the National Reactor Testing Station in Idaho, the SL-1 reactor sat in its 11th day of scheduled shutdown. The stationary low-power reactor number 1, a 3-megawatt thermal boiling water reactor designed for remote military installations, required routine maintenance before restart. Primary coolant pressure held steady at atmospheric conditions. Control rods remained fully inserted in their shutdown positions. The reactor core, containing 93.2% enriched uranium-235 in 40 fuel assemblies, showed no unusual characteristics. 3 military operators, Army specialists Richard McKinley and John Burns, and Navy CB Richard Legg, prepared to reconnect control rod drive mechanisms that had been disconnected for maintenance. The procedure required manual withdrawal of the central control rod approximately 4 inches to engage the drive coupling. This task had been performed routinely by trained personnel. The reactor's designers had incorporated standard safety margins. Multiple control rods provided redundant shutdown capability. Steam formation would terminate any inadvertent criticality through negative reactivity feedback. Yet the SL-1's design contained a fundamental assumption that no single control rod could generate sufficient excess reactivity to achieve prompt criticality when manually withdrawn. This assumption proved incorrect. The decision to operate with only 40 of 59 possible fuel assemblies had concentrated the neutron flux toward the reactor's center, dramatically increasing the reactivity worth of the central control rod beyond design calculations. On the evening of January 3, 1961, at the National Reactor Testing Station in Idaho, the SL-1 reactor sat in its 11th day of scheduled shutdown. The stationary low-power reactor number 1, a 3-megawatt thermal boiling water reactor designed for remote military installations, required routine maintenance before restart. Primary coolant pressure held steady at atmospheric conditions. Control rods remained fully inserted in their shutdown positions. The reactor core, containing 93.2% enriched uranium-235 in 40 fuel assemblies, showed no unusual characteristics. 3 military operators, Army specialists Richard McKinley and John Burns, and Navy CB Richard Legg, prepared to reconnect control rod drive mechanisms that had been disconnected for maintenance. The procedure required manual withdrawal of the central control rod approximately 4 inches to engage the drive coupling. This task had been performed routinely by trained personnel. The reactor's designers had incorporated standard safety margins. Multiple control rods provided redundant shutdown capability. Steam formation would terminate any inadvertent criticality through negative reactivity feedback. Yet the SL-1's design contained a fundamental assumption that no single control rod could generate sufficient excess reactivity to achieve prompt criticality when manually withdrawn. This assumption proved incorrect. The decision to operate with only 40 of 59 possible fuel assemblies had concentrated the neutron flux toward the reactor's center, dramatically increasing the reactivity worth of the central control rod beyond design calculations. How could a safety system designed to prevent accidents guarantee catastrophic failure through the very procedures meant to maintain it? The SL-1 reactor emerged from the U.S. Army's recognition that conventional diesel generators and boilers, supporting remote radar installations in Arctic regions, presented significant logistical challenges. From 1954 to 1955, the Army Reactors Branch had evaluated requirements for nuclear reactor plants capable of operating in regions where fuel delivery was expensive, dangerous, and weather-dependent. The specifications reflected military priorities. All components must be transportable by air, limited to packages measuring 7.5 by 9 by 20 feet and weighing no more than 20,000 pounds. The reactor design prioritized simplicity, reliability, and minimal on-site construction over redundant safety systems. Argonne National Laboratory received the contract to design what would initially be called the Argonne Low-Power Reactor. The design team used experience from the borax experiments as their foundation, but the military requirements fundamentally altered the safety philosophy embedded in civilian reactor development. Where commercial reactors incorporated multiple independent safety systems and assumed trained operator supervision, The Army's specifications demanded a reactor that could function with minimal technical oversight in harsh environments. This constraint would prove decisive. The ALPR design represented a compromise between nuclear safety principles and operational necessities. The reactor utilized a boiling water design with natural circulation, eliminating the need for complex pumping systems that might fail in remote locations. Light water served as both coolant and neutron moderator. The circulating water system operated at 300 pounds per square inch, flowing through fuel plates of uranium-aluminum alloy. These design choices reflected proven technology from the Borax program, but the scaling and operational requirements introduced new variables. Central to the reactor's control philosophy was the assumption that the reactor core would contain 59 fuel assemblies arranged in a standard configuration. Under this design premise, 9 control rods would provide reactivity control, 5 active cruciform rods, and 4 positioned as backups or test locations. The control rods were fabricated from 60 mils thick cadmium, clad with 80 mils of aluminum, with an overall span of 14 inches and an effective length of 32 inches. In the designed configuration, the central control rod, designated rod number 9, would possess sufficient reactivity worth to control normal operations while remaining well below the threshold for prompt criticality. However, the decision to load only 40 fuel assemblies fundamentally altered the neutron flux distribution within the core. This modification was driven by cost considerations and the prototype nature of the installation, but its implications for control rod reactivity were inadequately analyzed. The reduced fuel loading created a more compact, neutronically active core concentrated toward the center where Rod 9 was positioned. Post-accident calculations would determine that this configuration increased Rod 9's reactivity worth from approximately 3% deltac under full loading to 4.4% deltac in the actual 40-assembly configuration. The significance of this increase cannot be overstated. In thermal neutron reactors, prompt criticality occurs when the multiplication factor exceeds 1 by the delayed neutron fraction, approximately 0.65% for highly enriched uranium systems like SL-1. The design assumption that Rod 9 could not achieve prompt criticality was based on calculations for the full 59 assembly core. With only 40 assemblies loaded, Rod 9 possessed more than 6 times the excess reactivity required for prompt criticality. This miscalculation reflected a broader philosophical gap in the reactor safety approach. The SL-1 design team operated under peacetime nuclear development assumptions, where multiple barriers prevented accidents: trained operators, detailed procedures, supervisory oversight, and conservative operating practices. The military requirement for simplicity and autonomous operation conflicted with these assumptions, but the design calculations were not updated to reflect the new operational reality. The control room instrumentation reflected this optimistic design philosophy. The reactor was equipped with standard neutron flux monitors, temperature indicators, and pressure gauges appropriate for normal operations. However, the instrument ranges and alarm setpoints assumed that operators would recognize and respond to developing transients over time frames measured in minutes or seconds. No instrumentation existed to detect or respond to excursions developing in milliseconds. The assumption that such rapid excursions were physically impossible eliminated any perceived need for fast-acting protection systems. Training protocols reinforced these design assumptions. Military personnel trained on reactor operations focused on normal startup, power operation, and routine shutdown procedures. Scenario-based training emphasized responses to gradual transients, loss of circulation, minor reactivity insertions, equipment failures that developed over observable timeframes. The possibility that routine maintenance could trigger instantaneous, irreversible core damage was not addressed because the design calculations indicated such scenarios were impossible. The procedural framework surrounding control rod maintenance embodied similar optimistic assumptions. Maintenance procedures specified that control rods should be withdrawn manually by several inches to reconnect drive mechanisms following scheduled shutdowns. These procedures had been performed hundreds of times without incident by experienced operators. The process was considered routine because the design calculations indicated that even complete withdrawal of a single control rod would not threaten reactor safety. No independent verification was required. No special precautions were mandated. The procedure was classified as standard maintenance rather than safety-critical operation. Organizational factors further reinforced these design assumptions. Combustion Engineering Incorporated, the contractor responsible for day-to-day operations, maintained supervisory staff during normal working hours but not around the clock. The Atomic Energy Commission and Army Reactors Office believed that continuous supervision would undermine the military's goal of developing autonomous reactor operation capabilities. This decision reflected confidence in the inherent safety of the design and the routine nature of maintenance operations. The reactor building itself embodied the design philosophy's limitations. The cylindrical steel structure measured 38.5 feet in diameter with an overall height of 48 feet, constructed primarily of quarter-inch plate steel. This building was not designed as a pressure containment structure comparable to those required for reactors in populated areas. The assumption that energetic releases were impossible made such robust containment appear unnecessary. The building could contain normal operational releases and minor equipment failures, but was not engineered to withstand the pressures and forces associated with rapid energy deposition in the reactor core. By early 1961, several indicators suggested that the design assumptions required reassessment. Control rod sticking incidents had increased dramatically in the final months of operation. From November 1960 through December 1960, 23 stuck control rod incidents occurred, representing a 13% failure rate compared to the historical 2.5% rate. Rod 9, despite having the best operational record, was operated more frequently than other control rods due to its central importance in reactivity control. However, these performance degradations were interpreted as routine mechanical problems rather than symptoms of a fundamental design vulnerability. The increasing frequency of control rod problems reflected normal wear and corrosion in the reactor's operating environment. Misalignment, corrosion product buildup, bearing wear, clutch wear, and drive mechanism seal wear all contributed to mechanical difficulties. Plant management understood these problems as maintenance issues requiring attention during scheduled outages, not as safety concerns that might affect manual rod operations. The mechanical problems were seen as separate from the reactor physics assumptions that governed safety analysis. Post-accident investigation would reveal that these mechanical and design issues were causally linked. The increased control rod sticking created operational pressures to exercise rods manually to maintain smooth operation. Operators developed informal techniques for freeing stuck rods through manipulation of the control rod assemblies. These practices, while effective for resolving mechanical problems, were not analyzed for their potential reactivity consequences. The combination of increased mechanical problems and informal operational responses created conditions where routine maintenance could interact with design vulnerabilities. The fundamental design assumption that single control rod worth could not achieve prompt criticality created a false sense of security that permeated every aspect of SL-1 operations. Training, procedures, supervision, and safety analysis all reflected confidence in this assumption. When the assumption proved incorrect, none of the defensive barriers remained effective. The reactor's safety was entirely dependent on the accuracy of calculations that had not been updated to reflect the actual core loading configuration. The SL-1 design represented state-of-the-art nuclear engineering for its intended purpose, but it embodied assumptions about reactor behavior that were not validated under the actual operating configuration. The drive for operational simplicity and autonomous operation created a reactor design where single-point failures could defeat all safety systems simultaneously. The military requirements for transportability and minimal supervision were achievable, but only by accepting risks that were not fully recognized at the time. This design philosophy would prove inadequate when confronted with the reality of nuclear physics, operating outside the assumed parameters. The gap between design assumptions and physical reality created conditions where routine procedures could trigger catastrophic consequences. Understanding this gap requires examining not just the technical specifications, but the organizational and operational context that made the design assumptions appear reasonable to competent engineers and experienced operators. The reactor that sat ready for maintenance on January 3, 1961, was the product of careful engineering and extensive testing. Every system had been validated against design requirements, every procedure had been performed successfully, every safety assumption had been confirmed through analysis and experience, yet these accomplishments had been achieved within a framework of assumptions that were about to be tested beyond their limits. The reactor was simultaneously a successful prototype and a nuclear device whose true behavior under certain conditions remained unknown to those who operated it. The mechanical degradation that characterized SL-1's final months of operation created a web of latent conditions that would prove decisive on January 3, 1961. Between November 18 and December 23, 1960, 23 control rod sticking incidents occurred during routine testing procedures, a failure rate of 13% compared to the historical average of 2.5% observed from February 1959 through November 1960. This dramatic increase represented more than statistical variation. It indicated systematic degradation in control rod drive mechanisms that required increasingly frequent manual intervention. The control rod sticking phenomenon manifested in multiple ways throughout the reactor's operational history. From February 1959 to December 1960, 43 separate incidents of control rod sticking occurred during scram and rod drop tests, with an additional 21 rod sticking incidents during routine operations. 4 of these operational failures occurred during the final month of operation, indicating accelerating mechanical problems as the reactor approached its scheduled maintenance period. The pattern suggested that normal wear mechanisms, bearing degradation, clutch wear, corrosion product accumulation, and drive mechanism seal deterioration, were approaching critical thresholds. However, the interpretation of these mechanical problems reflected a fundamental disconnect between operational reality and safety analysis assumptions. Plant management treated control rod sticking as a maintenance issue requiring mechanical correction, not as a safety concern that might affect the reactor's nuclear characteristics. The increasing frequency of manual interventions to free stuck control rods was seen as an operational inconvenience, rather than an indication that routine procedures were being performed under conditions not envisioned in the original design analysis. The procedural response to control rod sticking problems created additional latent vulnerabilities. Operators developed informal techniques for exercising stuck control rods to restore normal operation. These techniques included manual manipulation of control rod assemblies to overcome mechanical binding and corrosion effects. The procedures were effective at resolving immediate operational problems and had been performed successfully hundreds of times by experienced personnel. However, these informal procedures were not subjected to the same safety analysis as formal operating procedures, creating gaps in the understanding of potential consequences. The human factors implications of increasing control rod problems extended beyond simple mechanical considerations. As control rods became more difficult to operate reliably, operators necessarily became more familiar with manual manipulation techniques. This familiarity bred confidence in the procedures and reduced perceived risk. Operators who had successfully freed stuck control rods numerous times without incident naturally developed confidence that these techniques were inherently safe. The success of previous interventions reinforced the belief that manual control rod operations posed no significant nuclear safety risks. Organizational factors further amplified these latent conditions. The decision to limit combustion engineering supervision to normal working hours reflected budgetary constraints but eliminated a crucial layer of technical oversight during off-shift operations. The Atomic Energy Commission and Army Reactors Office explicitly rejected around-the-clock supervision because they believed it would undermine the military's objective of developing autonomous reactor operation capabilities. This decision reflected confidence in the reactor design's inherent safety and the routine nature of maintenance operations. The absence of continuous technical supervision created conditions where informal procedures could evolve without engineering review. Operators working during evening and weekend shifts necessarily relied on their own judgment and experience when mechanical problems arose. While these operators were well-trained and experienced, they lacked the broader technical perspective that engineering supervision might have provided. The organizational structure assumed that routine maintenance operations posed minimal risk and required minimal oversight, assumptions that proved inadequate when routine procedures encountered design vulnerabilities. Training protocols reinforced these organizational assumptions by emphasizing normal operations over accident scenarios. Military personnel received extensive training in reactor startup, power operation, and routine shutdown procedures. The training focused on scenarios where reactor behavior could be predicted and controlled through established procedures. Emergency training emphasized responses to gradual transients that developed over timeframes, allowing deliberate analysis and response. The possibility that routine maintenance could trigger rapid, irreversible consequences was not addressed because the design analysis indicated such scenarios were impossible. The training emphasis reflected broader assumptions about reactor behavior that permeated the nuclear industry during this period. Reactor training programs focused on normal operations and gradual transients because these scenarios encompass the vast majority of operational experience. Rapid excursions were considered extremely unlikely based on reactor physics principles and design analysis. Training time devoted to scenarios that were believed to be physically impossible was seen as less valuable than training focused on realistic operational challenges. However, this training philosophy created cognitive biases that would prove significant during the accident. Operators were extensively trained to recognize and respond to gradual changes in reactor parameters. They developed mental models of reactor behavior based on scenarios where changes occurred over minutes or hours, allowing time for analysis, consultation, and deliberate response. These mental models were accurate for the scenarios they addressed, but they did not encompass the possibility of changes occurring faster than human response times. The maintenance procedures themselves embodied assumptions that created additional latent vulnerabilities. The procedure for reconnecting control rod drive mechanisms was classified as routine maintenance rather than safety-critical operation. This classification reflected the engineering judgment that manual control rod withdrawal by the specified distance posed no safety concerns. The procedure required withdrawal of the central control rod by approximately 4 inches to engage the drive coupling, a distance well within the assumed safe operating envelope. The procedural classification had important implications for safety analysis and verification requirements. Routine maintenance procedures typically did not require independent verification or special precautions beyond normal industrial safety practices. The assumption that single control rod manipulation could not threaten reactor safety eliminated the perceived need for additional procedural safeguards. Multiple operators could perform the procedure without independent confirmation because the consequences of errors were assumed to be minimal. The procedure's apparent simplicity masked underlying complexities that were not fully appreciated. While the required control rod movement was precisely specified, the procedure did not account for mechanical conditions that might make precise positioning difficult. Operators performing the procedure on equipment with known sticking problems necessarily relied on their judgment to determine when adequate withdrawal had been achieved. The procedure assumed that operators could easily distinguish between the required 4-inch withdrawal and potentially dangerous excessive withdrawal, but this assumption had not been tested under the degraded mechanical conditions existing in early 1961. The increasing control rod problems also created time pressures that affected procedural compliance. As mechanical problems became more frequent and severe, maintenance operations required more time and effort to complete successfully. Operators working under schedule pressure to restore the reactor to operational status might naturally focus on achieving functional objectives rather than precise adherence to procedural details. The pressure to complete maintenance efficiently could encourage shortcuts or informal techniques that appeared effective based on previous experience. Physical factors in the control room environment contributed additional latent conditions. The manual control rod withdrawal procedure required operators to work in close proximity to the reactor vessel during maintenance periods. The control rod drive mechanisms were located directly above the reactor core, requiring operators to position themselves over the reactor during the reconnection procedure. This positioning was necessary for the maintenance task, but placed operators in locations where they would be directly exposed to any energetic release from the reactor core. The control room design reflected assumptions about the types of hazards operators might encounter during maintenance operations. The room was designed to protect operators from routine radiation exposure and normal industrial hazards. However, the design did not incorporate protection against rapid energy releases because such events were considered physically impossible. The assumption that maintenance operations posed only routine hazards eliminated the perceived need for additional protective measures. Instrumentation systems reinforced these assumptions by providing information appropriate for normal operations but inadequate for detecting rapid changes in reactor status. The neutron monitoring systems were designed to track gradual changes in reactor power over timeframes measured in seconds or minutes. The instruments could not detect or display changes occurring in milliseconds, creating gaps in the operator's ability to monitor reactor status during rapid transients. The instrumentation was entirely adequate for its intended purpose, but could not provide useful information during events that developed faster than instrument response times. The alarm systems shared similar limitations. Alarm set points and response times were established based on scenarios where operators would have time to analyze conditions and implement corrective actions. The alarm systems assumed that dangerous conditions would develop gradually, allowing operators to recognize problems and respond appropriately. Alarms that activated during rapid transients would provide information about consequences rather than warnings that might prevent accidents. Communication systems and emergency response procedures embodied comparable assumptions about accident scenarios. Emergency response plans assumed that reactor accidents would involve gradual deterioration, allowing time for analysis, consultation with technical experts, and coordinated response. The procedures did not address scenarios where immediate, irreversible consequences occurred before operators could implement any protective actions. The emergency response framework was designed for accidents that developed over hours or days, not events that were completed in milliseconds. The integration of these latent conditions created a system where multiple assumptions had to remain valid simultaneously for safe operation to continue. The increasing control rod mechanical problems challenged operational assumptions but not safety analysis assumptions. The organizational decision to limit supervision reflected confidence in design assumptions. The training emphasis on gradual transients reflected assumptions about physically possible accident scenarios. The procedural classification reflected assumptions about single-failure consequences. The instrumentation and emergency response systems reflected assumptions about accident development timescales. Each of these assumptions was individually reasonable based on the available information and experience. However, their integration created a system where the failure of any single assumption could cascade through multiple defensive barriers simultaneously. The reactor's safety depended not just on the reliability of individual components or procedures, but on the continued validity of the entire framework of assumptions that governed its design and operation. By January 1961, several of these assumptions were being challenged by operational experience, but the challenges were interpreted within the existing framework, rather than as indicators that the framework itself might be inadequate. The increasing control rod problems were seen as mechanical issues, requiring attention during the scheduled maintenance period. The procedural adaptations were seen as evidence of operational flexibility and competence. The organizational arrangements were seen as appropriate for the reactor's inherent safety characteristics. The maintenance period beginning in late December 1960 provided an opportunity to address known mechanical problems and restore the reactor to optimal operating condition. However, the same period also created conditions where latent vulnerabilities could interact with routine procedures in ways that had not been anticipated. The combination of degraded mechanical conditions, informal procedural adaptations, limited supervision, and design vulnerabilities created a configuration where routine maintenance could trigger consequences far beyond anything envisioned in the original safety analysis. 9:01 p.m. Mountain Standard Time on January 3, 1961, the SL-1 reactor transitioned from a stable shutdown condition to prompt criticality in less than 4 milliseconds. The initiating event, the manual withdrawal of control rod number 9 during a routine maintenance procedure, represented the convergence of design vulnerabilities, mechanical degradation, and human factors that had been developing over months of operation. What began as a standard reconnection procedure became an irreversible nuclear excursion that would kill all 3 operators and destroy the reactor core. The evening of January 3 had proceeded routinely until the moment of the accident. Army specialists Richard McKinley and John Burns, along with Navy CB Richard Legg, were preparing the reactor for restart after an 11-day shutdown period. The maintenance schedule required reconnection of control rod drive mechanisms that had been disconnected for inspection and servicing. This procedure had been performed hundreds of times without incident by trained military personnel. The operators had completed similar tasks throughout their assignment to SL-1 and possessed extensive experience with the reactor's mechanical systems. The specific task confronting the operators involved control rod number 9, the central control rod that provided primary reactivity control for the reactor. The maintenance procedure required manual withdrawal of this rod by approximately 4 inches to engage the automatic drive coupling mechanism. This withdrawal distance had been established through engineering analysis and operational experience as adequate for mechanical engagement while maintaining substantial safety margins. The procedure was considered routine because design calculations indicated that even complete withdrawal of a single control rod could not threaten reactor safety. However, post-accident forensic analysis would reveal that the actual rod withdrawal exceeded the procedural requirement by a factor of 5. Physical examination of control rod number 9 revealed scratches and wear patterns indicating withdrawal of approximately 20 inches rather than the specified 4 inches. This excessive withdrawal represented a human error of extraordinary magnitude, but the error occurred within a system designed to accommodate such mistakes without catastrophic consequences. The reactor's safety was supposed to be ensured by physics, not perfect human performance. The 20-inch withdrawal of control rod number 9 inserted approximately 4.4% excess reactivity into the SL-1 core, creating a supercritical condition that exceeded the delayed neutron fraction of 0.65% by more than a factor of 6. This reactivity insertion was sufficient to achieve prompt criticality, a condition where the nuclear chain reaction becomes self-sustaining on prompt neutrons alone, without requiring the slower delayed neutrons that normally allow time for control system response. In prompt critical conditions, reactor power can double every 10 microseconds, creating power levels that increase faster than any mechanical system can respond. The mechanism by which 20 inches of rod withdrawal occurred during a procedure requiring only 4 inches remains a subject of investigation and speculation. Post-accident experiments using identical control rod assemblies demonstrated that the 48-pound central rod assembly could be rapidly withdrawn by a single operator under certain conditions. Mock-up tests showed that 3 operators could withdraw a simulated rod assembly 30 inches in various time intervals, confirming that rapid manual withdrawal was within human physical capabilities. Several theories emerged to explain the excessive withdrawal. The first possibility involved inadvertent withdrawal during an attempt to free a stuck control rod. If rod number 9 had become mechanically bound in its guide channel, an operator attempting to break it free might apply excessive force, causing sudden, uncontrolled movement when the binding released. This scenario was consistent with the increasing control rod problems that had plagued SL-1 during its final months of operation, and with informal procedures that had developed for dealing with stuck rods. A second possibility involved deliberate rod exercising to improve mechanical operation. Operators had developed techniques for manually cycling control rods through extended travel ranges to reduce sticking and improve smooth operation. If an operator decided to exercise rod number 9 beyond the procedural requirement, the excessive withdrawal might result from unfamiliarity with the rod's reactivity worth or from mechanical factors that made precise positioning difficult. The investigation also considered more disturbing possibilities, including intentional acts by one of the operators. Early speculation focused on potential sabotage or murder-suicide scenarios, possibly involving personal relationships among the operators or their families. However, extensive investigation found no credible evidence supporting intentional action. The operators had shown no signs of emotional distress, personal conflicts, or unusual behavior prior to the accident. Their personal and professional relationships appeared normal, and no motives for intentional action could be established. The most probable explanation, supported by physical evidence and experimental analysis, involved accidental withdrawal during routine maintenance procedures performed under degraded mechanical conditions. Operator John Burns, identified as the individual performing the rod withdrawal based on his position in the reactor room and the nature of his injuries, likely encountered mechanical resistance while attempting the routine reconnection procedure. When the resistance was overcome through additional force, the control rod moved further than intended, inserting fatal amounts of excess reactivity. This scenario was consistent with the operational experience of increasing control rod problems and the informal techniques that had evolved for dealing with mechanical difficulties. It also explained why an experienced operator would perform an action with catastrophic consequences. The action was intended to be routine maintenance, not a safety-critical operation. The operator's mental model of the task focused on achieving mechanical objectives rather than nuclear safety considerations because the design analysis had indicated that nuclear safety was automatically ensured regardless of mechanical manipulations. The 4-millisecond interval between excessive rod withdrawal and prompt criticality provided no opportunity for human intervention or automatic safety system response. The reactor's neutron monitoring instruments detected the rising neutron flux, but the rate of increase exceeded their ability to provide useful information to operators. Alarm systems activated, but the alarms indicated consequences rather than providing warnings that might prevent the accident. The reactor's design incorporated automatic shutdown systems, but these systems were calibrated to respond to gradual transients, not to events developing in milliseconds. Within the first milliseconds of the prompt critical condition, nuclear fission rates in the reactor core increased exponentially. The energy deposition in the fuel elements caused rapid heating, thermal expansion, and steam formation. However, the negative reactivity feedback from these physical changes was insufficient to terminate the excursion before substantial energy release occurred. The reactor's design depended on steam formation to provide negative feedback that would limit power excursions, but the rapid energy deposition rate overwhelmed this passive safety mechanism. By 6 milliseconds after the initial rod withdrawal, steam formation had begun in the reactor core, but the reactivity insertion was so large that steam feedback could not overcome the excess reactivity quickly enough to prevent catastrophic energy release. The reactor power level reached approximately 20,000 megawatts, more than 6,000 times its design power rating. This enormous power density caused localized fuel melting and explosive vaporization in the most reactive regions of the core. The energy released during the first few milliseconds of the excursion converted water in the reactor core to superheated steam at extremely high pressure. The rapid steam formation created a pressure wave that propagated through the reactor coolant system, striking structural components with forces far exceeding design limits. The pressure pulse measured approximately 10,000 pounds per square inch at peak intensity, with average pressures around 500 pounds per square inch maintained over several milliseconds. Heat sensors positioned above the reactor vessel detected the energy release and triggered alarm systems at exactly 9:01 p.m., providing precise timing for the accident initiation. The sensors had experienced false alarms earlier that day during routine testing activities, creating a background of alarm system unreliability that would affect initial emergency response. However, the heat sensor readings on January 3 represented genuine detection of massive energy release from the reactor core. The physical mechanisms terminating the nuclear excursion involved catastrophic destruction of the reactor core geometry, rather than controlled shutdown through design safety systems. Post-accident analysis indicated that the nuclear chain reaction ended approximately 7.5 milliseconds after initiation, when fuel vaporization and core disassembly reduced reactivity below critical levels. The reactor achieved shutdown not through steam formation or control rod insertion, but through violent ejection of fissile material from the active core region. This termination mechanism represented complete failure of all design safety systems and protective features. The reactor's safety depended on maintaining core geometry and coolant inventory under all credible accident conditions. The SL-1 excursion destroyed both core geometry and coolant inventory simultaneously, eliminating the physical basis for controlled reactor operation. The shutdown occurred through mechanisms that also guaranteed destruction of the reactor and lethal radiation exposure to personnel in the immediate vicinity. The energy release during the excursion was estimated at approximately 133 megajoules, equivalent to 32 kilograms of conventional explosives. This energy was deposited in the reactor core within milliseconds, creating internal pressures that ejected the reactor vessel from its foundation and launched reactor components through the reactor building. The energy density was sufficient to melt and vaporize portions of the fuel elements, while simultaneously creating mechanical forces that destroyed the reactor's structural integrity. The sequence of events from routine maintenance to catastrophic core destruction occupied less than 10 milliseconds total. During this interval, the reactor transitioned from a safe shutdown condition through prompt criticality to core destruction and radioactive material release. The rapidity of this sequence eliminated any possibility of human intervention or automatic system response that might have prevented or mitigated the consequences. The accident developed faster than the response times of any protective systems incorporated in the reactor design. The divergence from expected reality began with the human error of excessive control rod withdrawal, but the consequences of that error were determined by reactor physics operating outside the design assumptions. The operators believed they were performing routine maintenance on a reactor designed to accommodate human mistakes without safety consequences. The reactor physics demonstrated that this belief was incorrect under the actual core loading configuration. The gap between perception and reality was measured in reactivity units and response times, creating conditions where routine procedures could trigger irreversible consequences. By 9:01 p.m. and 4 milliseconds, the SL-1 reactor had transitioned from a shutdown prototype to a destroyed nuclear device. The three operators in the reactor building had unknowingly participated in an uncontrolled nuclear excursion that would serve as a watershed event in reactor safety development. The routine maintenance procedure they had attempted to perform had become the initiating event for the only reactor accident in United States history to cause immediate operator fatalities. The nuclear excursion that began at 9:01 p.m. on January 3, 1961, unfolded according to fundamental physics principles that overwhelmed every safety assumption embedded in the SL-1 design. Within the first 4 milliseconds after control rod withdrawal, the reactor achieved a supercritical state that generated energy at rates far exceeding any mechanism for control or containment. The failure chain that followed represented not a cascade of equipment malfunctions, but the inexorable operation of nuclear physics under conditions that the reactor's designers had believed impossible. The initial reactivity insertion of approximately 4.4% delta K created a neutron multiplication factor of 1.044 in a system where the delayed neutron fraction was only 0.0065. This meant the reactor became supercritical on prompt neutrons alone by a factor of more than 6. In such conditions, the neutron population doubles approximately every 10 microseconds, creating exponential power growth that can increase reactor power by factors of thousands within milliseconds. No mechanical or human response system can operate effectively on such timescales. During the first millisecond, following rod withdrawal, neutron flux in the reactor core increased from shutdown levels to approximately 10 to the power of 16 neutrons per square centimeter per second. This flux level represented normal full power operation for the SL-1 design. However, the exponential growth rate meant that power levels continued increasing without any mechanism for immediate termination. The reactor's control systems, designed to respond to gradual power changes over seconds or minutes, provided no protection against excursions developing in milliseconds. By the second millisecond, reactor power had exceeded design levels by orders of magnitude. Energy deposition in the uranium-aluminum fuel plates began causing rapid temperature increases in the most reactive regions of the core. The fuel plate design incorporated aluminum cladding over uranium-aluminum alloy meat, with water gaps between plates for cooling and neutron moderation. This design was adequate for normal operation but could not accommodate the energy deposition rates occurring during the excursion. Temperature rise in the fuel plates followed the power increase with only slight delay due to thermal inertia. Post-accident analysis indicated that fuel temperatures in the central core region reached melting points for aluminum within 3 to 4 milliseconds of the initial rod withdrawal. The rapid heating caused thermal expansion of fuel plates and adjacent structures, creating mechanical stresses that exceeded design limits for reactor internal components. The reactor's passive safety systems depended on steam formation to provide negative reactivity feedback that would limit power excursions. As water in the core began heating toward saturation temperature, steam bubbles would normally form in the water channels between fuel plates. Steam has lower neutron moderating capability than liquid water, so steam formation reduces the probability of neutron-induced fission and provides negative reactivity feedback. This mechanism had been demonstrated successfully in previous borax experiments and formed the basis for SL-1 safety analysis. However, the magnitude of the reactivity insertion in SL-1 exceeded the capability of steam feedback to provide timely shutdown. Steam formation began approximately 6 milliseconds after the initial rod withdrawal, but by this time, the reactor power level had reached nearly 20,000 megawatts, more than 6,000 times the design power rating. The negative reactivity from steam formation was insufficient to overcome the 4.4% positive reactivity insertion before catastrophic energy deposition occurred in the fuel elements. The energy release rate during the peak of the excursion reached approximately 20 billion watts, concentrated in a core volume of less than 1 cubic meter. This power density was sufficient to rapidly heat fuel elements beyond their melting points and to create explosive vaporization of aluminum and uranium components. The vaporization process absorbed energy and contributed to termination of the nuclear chain reaction, but the energy required for vaporization was extracted from the fuel elements themselves, guaranteeing their destruction. Post-accident examination revealed that portions of the fuel plates in the central core region had been completely vaporized during the excursion. The vaporization process occurred rapidly enough to create substantial internal pressures within the reactor core. These pressures propagated through the coolant system as pressure waves that struck structural components with forces far exceeding their design limits. The pressure pulse represented conversion of nuclear energy to mechanical energy through rapid steam formation and fuel vaporization. The pressure wave generated by fuel vaporization and steam formation reached the top of the reactor vessel within approximately 8 milliseconds of the initial rod withdrawal. The wave struck the reactor vessel head with a peak pressure estimated at 10,000 pounds per square inch, creating forces equivalent to millions of pounds acting on the vessel structure. The reactor vessel, designed to contain normal operating pressures of 300 pounds per square inch, could not withstand these extreme loads. The reactor vessel responded to the pressure pulse by accelerating upward from its foundation. Post-accident measurements indicated that the 26,000-pound reactor vessel achieved an upward velocity of 27 feet per second, sufficient to lift the entire assembly 9 feet and 1 inch above its normal position. The vessel's upward travel was terminated when structural components struck the overhead crane system in the reactor building, preventing further vertical displacement. Simultaneously with vessel displacement, the pressure pulse ejected reactor shield plugs from the top of the reactor vessel at velocities approaching 85 feet per second. These shield plugs, weighing hundreds of pounds each, became projectiles within the reactor building. One shield plug struck operator Richard Legg, who was positioned on top of the reactor vessel during the maintenance procedure, driving completely through his body and pinning him to the ceiling of the reactor building. The explosive force that displaced the reactor vessel and ejected shield plugs also launched massive quantities of highly radioactive water, steam, and reactor core debris throughout the reactor building. The pressure release vented approximately 1,100 curies of fission products into the building atmosphere, including isotopes of xenon, krypton, strontium-91, and yttrium-91. An additional 80 curies of iodine-131 were released, creating serious contamination problems within the building and requiring extensive cleanup operations. The termination of the nuclear chain reaction occurred approximately 7.5 milliseconds after initiation through catastrophic disassembly of the reactor core geometry. The violent ejection of water, steam, and fuel debris reduced the neutron multiplication factor below critical levels by removing fissile material from the active core region and by eliminating the water moderation necessary for sustaining the chain reaction. The shutdown mechanism represented complete failure of the reactor as a controlled device rather than successful operation of designed safety systems. Total energy release during the excursion was calculated at approximately 4.4 x 1018 fissions, equivalent to 133 megajoules, or the explosive energy of 32 kilograms of TNT. This energy was deposited in the reactor core within milliseconds, creating the mechanical forces that destroyed the reactor structure and killed the 3 operators. However, the energy release was insufficient to create significant amounts of corium, or to threaten the reactor vessel's structural integrity beyond the mechanical damage caused by pressure forces. The rapid termination of the excursion through core disassembly prevented more severe consequences that might have resulted from sustained power operation at extreme levels. If the nuclear chain reaction had continued for seconds rather than milliseconds, the energy release could have been sufficient to breach the reactor vessel and create more extensive radioactive material dispersion. The violent shutdown mechanism, while catastrophic for the reactor and operators, actually limited the total energy release and radiological consequences. Post-accident analysis revealed that very little molten fuel material was recovered from the reactor core, despite the extreme energy deposition rates experienced during the excursion. The fuel plates showed evidence of catastrophic destruction with extensive voids where material had been vaporized, but investigators found no significant amounts of glazed molten material characteristic of severe reactor accidents. The rapid cooling provided by water injection and steam formation prevented formation of substantial quantities of molten debris. The absence of significant corium formation indicated that the core destruction occurred through explosive vaporization rather than gradual melting and relocation. This mechanism dispersed fissile material throughout the reactor building rather than concentrating it in locations where continued fission might occur. The dispersal pattern was consistent with rapid pressure-driven ejection rather than gravity-driven flow of molten materials. Forensic examination of reactor components provided detailed evidence of the excursion's progression and termination mechanisms. Neutron activation of metal components throughout the reactor building confirmed that intense neutron fluxes had occurred during the excursion. Analysis of activated materials in the operator's personal effects, including copper-64 from a cigarette lighter, gold-198 from a wedding ring, and brass components from watch bands, provided quantitative confirmation of the neutron fluences experienced during the accident. These neutron activation measurements also confirmed the locations of the 3 operators during the excursion and provided estimates of the total number of fissions that occurred. The activation patterns were consistent with intense neutron radiation emanating from the reactor core during the brief period of supercritical operation. The measurements ruled out alternative explanations for the accident, such as chemical explosions or conventional mechanical failures that might have produced similar physical damage without neutron radiation. The reactor building structure contained most of the radioactive material released during the accident, despite not being designed as a pressure containment system. The building's ability to limit radioactive material dispersion was fortuitous rather than planned, as the designers had not anticipated accident scenarios requiring containment of energetic releases. The building's performance during the accident influenced subsequent reactor designs to incorporate more robust containment systems capable of withstanding design basis accidents. Environmental monitoring following the accident detected fission products at locations downwind from the reactor building, confirming that some radioactive material had escaped the building during the excursion. However, the quantities released to the environment were relatively small compared to the total core inventory, and the remote location of the facility limited public exposure. The environmental impact was considered manageable given the reactor's location in the sparsely populated high desert of eastern Idaho. The failure chain that destroyed SL-1 demonstrated the fundamental importance of reactivity control in reactor safety. Once excessive reactivity was inserted through rod withdrawal, no subsequent actions or automatic systems could prevent catastrophic consequences. The reactor's safety depended entirely on preventing large reactivity insertions rather than controlling or mitigating their consequences. This lesson would fundamentally change reactor safety philosophy and design requirements for future nuclear facilities. The physics autopsy of the SL-1 accident revealed that the reactor behaved exactly as nuclear physics predicted under the conditions that actually existed, rather than the conditions assumed in the safety analysis. The accident resulted from accurate physics operating within an incorrect design assumption framework rather than from any failure of physical principles or unexpected phenomena. The reactor's destruction provided definitive proof that reactor safety must be based on preventing unacceptable conditions rather than assuming they cannot occur. The emergency response to the SL-1 accident began 9 minutes after the initial excursion, when 6 firefighters from the National Reactor Testing Station arrived expecting to investigate another false alarm. The response team, led by Assistant Chief Ken Dearden and including Lieutenant Mel Hess and firefighters Bob Archer, Carl Johnson, Egon Lamprecht, Gerald Stewart, and Vern Conlon, had responded to similar alarms earlier that day without finding any actual emergency. The pattern of false alarms created an initial presumption that January 3 would follow the same routine, a presumption that delayed recognition of the accident's severity. The firefighters' initial observations supported their expectation of a routine call. The reactor building showed only minimal external signs of disturbance, slight steam emissions that appeared normal for the cold 6 degrees Fahrenheit evening temperature. The building's external appearance provided no indication that a catastrophic nuclear excursion had occurred inside, that 3 men lay dead or dying within the structure, or that radiation levels inside the building exceeded safe exposure limits by factors of hundreds. Upon entering the support facilities building, the response team discovered the first indicators of unusual conditions. The building appeared normal but was completely unoccupied. 3 mugs of warm coffee sat in the break room with 3 jackets hanging nearby, suggesting that the operators had been present shortly before the accident and had expected to return. The scene indicated sudden, unexpected interruption of routine activities rather than planned departure or gradual evacuation. The firefighters' entry into the reactor control room revealed the first definitive indication of serious problems. A radiation warning light was illuminated on the control panel, indicating abnormal radiation levels somewhere in the facility. However, the significance of this warning was not immediately apparent to personnel whose training focused on conventional fire suppression rather than radiation emergency response. The warning light represented information rather than immediate danger to the response team, but it indicated that normal industrial safety procedures might be inadequate for the conditions they would encounter. The radiation detection equipment available to the initial response team provided the first quantitative indication of the accident's severity. As the firefighters climbed the stairs toward the reactor operating floor, their handheld radiation detector jumped sharply above its maximum range, indicating radiation levels exceeding the instrument's capability to measure. This reading prompted immediate retreat to obtain higher-range detection equipment, but it also confirmed that the situation involved significant radiation hazards rather than conventional industrial accidents. The second attempt to reach the reactor floor, using a detector with a 200 roentgens per hour maximum range, again exceeded the instrument's capability as the team ascended the stairs. These readings indicated radiation levels that posed immediate health risks to unprotected personnel and confirmed that access to the reactor area would require specialized equipment and procedures. The progressive failure of increasingly sophisticated radiation detection equipment demonstrated that the accident had created conditions far outside normal operational experience. At 9:17 p.m., 16 minutes after the initial excursion, health physicist personnel arrived to provide specialized expertise in radiation protection and emergency response. The involvement of health physics personnel marked the transition from conventional emergency response to radiation emergency procedures. But these procedures had been developed for scenarios involving gradual radiation releases, rather than instantaneous massive exposure events. The existing emergency response framework assumed that radiation accidents would provide time for assessment, planning, and coordinated response. The health physicists' initial reconnaissance, conducted with air tanks and positive pressure masks to prevent inhalation of radioactive materials, revealed radiation levels of 25 roentgens per hour at the base of the stairs leading to the reactor floor. These levels, while manageable for brief exposures, indicated that sustained work in the area would require careful exposure control and time limitations. However, the radiation levels increased dramatically with elevation, suggesting that conditions on the reactor floor itself would be substantially more hazardous. Using a higher-range ion chamber detector capable of reading up to 500 roentgens per hour, the health physicist and assistant chief Moschberger reached the top of the stairs and briefly observed the reactor room interior. Their detector immediately pegged at its maximum reading, indicating radiation levels exceeding 500 roentgens per hour throughout the reactor floor area. These levels posed immediate life-threatening risks and severely limited the time available for rescue operations or damage assessment. The visual observations from this initial reconnaissance revealed extensive physical damage throughout the reactor room. The operating floor was strewn with rocks, steel punchings, twisted metal debris, and other materials ejected during the excursion. The scene appeared dim and wet, with water covering much of the floor area. The extensive debris field indicated that substantial mechanical forces had acted throughout the room, but the specific nature and extent of damage could not be determined during brief observations under extreme radiation conditions. The arrival of lead SL-1 personnel, health physicist Ed Valario and operations supervisor Paul Duckworth, at approximately 10:30 p.m., provided specialized knowledge of the facility and its operations. However, their expertise had been developed for normal and abnormal operational conditions, not for accident scenarios involving core destruction and massive radiation releases. The emergency response was being conducted by personnel with relevant training and experience, but within a framework that had not anticipated the specific conditions created by the SL-1 accident. Valario and Duckworth's entry into the reactor building, conducted with air packs and emergency equipment, located the first victim approximately halfway up the stairs to the reactor floor. Specialist Richard McKinley was found alive but severely injured, bleeding, and in deep shock from trauma sustained during the excursion. The discovery of an injured survivor added urgency to the emergency response but also complicated radiation protection considerations, as medical treatment would require extended exposure times in high radiation areas. The rescue of McKinley required coordination between medical treatment and radiation protection objectives that had not been extensively rehearsed or planned. 5 health physicists joined Valario and Duckworth in attempting to remove Missy Kinley from the reactor building, but the operation was complicated by visibility problems caused by fogging airpack masks, mechanical debris that had to be cleared before McKinley could be moved, and equipment failures that left some rescuers without respiratory protection in contaminated areas. The rescue operation encountered immediate equipment reliability problems that demonstrated gaps between emergency response planning and operational reality. 2 of the Scott air packs worn by rescue personnel froze up and ceased functioning during the operation, forcing evacuation of one rescuer and leaving another to complete Missy Kinley's evacuation while breathing contaminated air directly. These equipment failures had not been anticipated in emergency procedures and illustrated the difficulty of conducting complex operations under the extreme conditions created by the accident. The evacuation of McKinley from the reactor building was completed in approximately 3 minutes, representing successful coordination under extremely challenging conditions. However, the evacuation immediately created secondary contamination problems that had not been fully anticipated in emergency planning. McKinley's clothing and body were heavily contaminated with radioactive materials, creating radiation exposure risks for medical personnel and contamination risks for medical facilities and transportation equipment. The contamination control problems extended beyond the immediate victim to encompass all personnel and equipment involved in the rescue operation. The ambulance used to transport McKinley became contaminated and had to be abandoned in the desert for several hours, until decontamination procedures could be implemented. medical personnel who treated Matt Kinley required immediate decontamination and radiation exposure monitoring. The emergency response had successfully rescued the surviving victim, but at the cost of creating widespread secondary contamination that would require extensive cleanup efforts. Matt Kinley's death during transport to medical facilities eliminated any possibility of obtaining first-hand information about the accident sequence from surviving personnel, but it also ended the immediate medical emergency that had driven the initial rescue efforts. However, the deaths of all three operators created new challenges for emergency response and accident investigation, as understanding the accident sequence would depend entirely on physical evidence rather than witness accounts. The discovery and recovery of the remaining two victims required additional emergency operations under even more severe radiation conditions. Specialist John Burns was located on the reactor floor, partially covered with steel pellets and blood from injuries sustained during the excursion. His recovery, accomplished on the night of January 4, required teams working in pairs with strict time limitations to minimize radiation exposure. The operation demonstrated the feasibility of conducting necessary work under high radiation conditions but confirmed that such operations required extensive planning and specialized procedures. The recovery of C.B. Richard Legg presented the most challenging technical problem of the emergency response. Legg had been impaled by reactor shield plug number 7 and pinned to the ceiling directly above the reactor vessel, requiring modification of the reactor room structure before recovery could be attempted. The operation required 4 days of planning and preparation, including installation of a welder inside a lead-shielded box attached to a crane to cut access openings in the ceiling structure. The final recovery operation, conducted on January 9th, used teams of 10 men working in relays with exposure times limited to 65 seconds each. Long poles with hooks were used to free Legg's body from the shield plug and drop it onto a stretcher system operated by crane from outside the building. The operation required precise coordination between multiple teams operating under severe time pressure, but it successfully completed the victim recovery phase of the emergency response without additional serious injury to rescue personnel. The extensive decontamination operations required throughout the emergency response demonstrated that existing facilities and procedures were inadequate for accidents involving major radiation releases. Approximately 30 first responders required immediate decontamination, including showers, scrubbing with potassium permanganate, and complete clothing changes. The scale of contamination exceeded the capacity of existing decontamination facilities and required improvised procedures and equipment to ensure adequate personnel protection. The emergency response to the SL-1 accident revealed fundamental limitations in both emergency planning and emergency response capabilities for severe reactor accidents. The existing emergency response framework had been developed for scenarios involving gradual development of hazardous conditions, allowing time for assessment, planning, and coordinated response. The instantaneous nature of the SL-1 accident eliminated these response opportunities and required improvised solutions to problems that had not been adequately anticipated. However, the emergency response also demonstrated remarkable competence and dedication by personnel operating under extreme conditions with inadequate preparation and equipment. 22 individuals received radiation exposures between 3 and 27 Röntgens during rescue and recovery operations, representing substantial health risks undertaken to protect others and to gather information necessary for understanding the accident. The emergency response succeeded in its immediate objectives of victim recovery and initial damage assessment, even though it revealed significant gaps in emergency preparedness. The radiation exposure received by emergency response personnel established precedents for acceptable risk levels during nuclear emergency operations. The exposure limits existing before the accident were 100 Röntgens to save a life and 25 Röntgens to save valuable property. The actual exposures during SL-1 emergency response remained within these guidelines, but the guidelines themselves had not been tested under conditions involving core destruction and massive radiation releases from reactor accidents. The secondary contamination problems created during emergency response operations would persist for months and years following the accident, requiring extensive environmental monitoring and cleanup operations. The contamination spread from the reactor building to support facilities, vehicles, equipment, and personnel, creating a complex remediation challenge that had not been anticipated in accident planning. The long-term consequences of emergency response decisions made under immediate time pressure would affect cleanup operations and personnel safety for the duration of the remediation effort. The forensic investigation of the SL-1 accident began immediately following emergency response operations and would continue for years, ultimately producing the most comprehensive analysis of a reactor accident in nuclear industry history. The investigation faced unprecedented challenges. All 3 operators were dead, the reactor core was destroyed, and radiation levels throughout the facility prevented normal investigative techniques. However, the accident also provided unique opportunities to examine nuclear safety assumptions through analysis of physical evidence that could not be disputed or misremembered. The primary forensic artifact that would define understanding of the accident was the physical condition of control rod number 9 following its recovery from the destroyed reactor core. Post-accident examination revealed distinctive scratch patterns and wear marks indicating withdrawal of approximately 20 inches, rather than the 4 inches specified in maintenance procedures. These physical marks represented irrefutable evidence of the mechanism that initiated the accident, eliminating speculation about sabotage, equipment failure, or other alternative explanations. The forensic analysis of control rod damage patterns was supplemented by experimental work using identical SL-1 control rod assemblies under controlled conditions. Investigators constructed mock-up systems using spare control rod actuator assemblies loaded with weights equivalent to the 84-pound total movable mass of the SL-1 control rod system in water. Multiple subjects were tested to determine whether rapid manual withdrawal of 20 inches was within normal human capability, and these tests confirmed that such withdrawal could be accomplished by a single operator under certain conditions. The experimental results demonstrated that control rod number 9 could be rapidly withdrawn by manual force, but they also revealed the critical importance of precise force application and timing. Test subjects who applied force gradually could control rod position accurately, while those who applied sudden force to overcome apparent resistance often achieved greater withdrawal than intended when the resistance was overcome. This pattern was consistent with an operator encountering mechanical binding and applying additional force to complete what was perceived as a routine procedure. Nuclear forensics provided definitive proof that a prompt critical excursion had occurred, ruling out alternative explanations, such as chemical explosions or conventional mechanical failures. Analysis of personal effects recovered from the 3 victims revealed neutron activation products that could only have been created by intense neutron radiation. Copper, 64, identified in a cigarette lighter screw, gold 198 in a wedding ring, and activated brass in watchband components provided quantitative measurements of neutron fluence experienced during the accident. The neutron activation analysis extended beyond simple detection to sophisticated reconstruction of accident conditions. Hair samples taken from the victims during autopsy procedures were analyzed for phosphorus-32 activity, allowing investigators to determine the relative positions of the 3 operators during the nuclear excursion and to estimate the total number of fissions that occurred. These measurements provided independent confirmation of accident timing and magnitude that could be compared with calculations based on reactor physics and damage assessment. Environmental monitoring in the vicinity of the reactor facility detected fission products, including strontium-91, a major fission product that confirmed nuclear fission rather than neutron activation as the source of radioactive contamination. Air sampling downstream from the reactor building identified gaseous fission products, including isotopes of xenon and krypton, providing additional confirmation of core damage and fission product release. The environmental evidence established the accident as a genuine nuclear excursion rather than a conventional industrial accident with radiological consequences. The forensic examination of reactor core debris provided detailed information about the physical processes that occurred during the excursion. Despite the extreme energy deposition rates experienced during the accident, investigators found remarkably little molten fuel material in the reactor vessel or throughout the reactor building. The fuel plates showed extensive evidence of catastrophic destruction with large voids where material had been vaporized, but very little glazed molten material characteristic of severe overheating was recovered. This absence of significant molten fuel indicated that core destruction had occurred through explosive vaporization rather than gradual melting and relocation. The rapid energy deposition had been sufficient to vaporize aluminum and uranium components directly from solid state, dispersing fissile material throughout the reactor building rather than concentrating it in locations where continued nuclear reaction might occur. The dispersal pattern confirmed that reactor shutdown had been achieved through geometry destruction rather than control rod insertion or steam formation. The reactor vessel examination revealed the extraordinary mechanical forces generated during the excursion. The 26,000-pound reactor vessel had been lifted 9 feet and 1 inch above its normal position by pressure forces generated within milliseconds of the initial rod withdrawal. Detailed analysis of vessel displacement and impact patterns confirmed peak pressures of approximately 10,000 pounds per square inch, with sustained pressures of 500 pounds per square inch, sufficient to accelerate the massive vessel structure. Forensic analysis of the reactor building structure itself provided information about energy release and containment effectiveness. The cylindrical steel building had contained most of the radioactive material released during the accident, despite not being designed as a pressure containment system. However, detailed examination revealed numerous penetrations and structural deformations that had allowed some radioactive material to escape to the environment. The building's performance established both the benefits and limitations of even minimal containment structures during severe accidents. The comprehensive forensic investigation ultimately ruled out all alternative explanations for the accident except accidental control rod withdrawal during routine maintenance procedures. Extensive investigation found no evidence supporting theories of deliberate operator action, mechanical equipment failure, or external intervention. The physical evidence consistently indicated human error in estimating rod withdrawal distance during a procedure that operators believed to be inherently safe. However, the forensic findings also established that the human error occurred within a system designed to accommodate such mistakes without catastrophic consequences. The reactor's safety was supposed to depend on physics rather than perfect human performance, and the accident demonstrated that this design philosophy was incorrect under the actual core loading configuration. The forensic evidence proved that the reactor design contained fundamental vulnerabilities that made catastrophic accidents possible through routine operational errors. The investigation's findings led to immediate and fundamental changes in reactor safety philosophy and regulatory requirements. The one-stuck rod criterion was implemented for all future reactor designs, requiring that reactors remain safely shut down even with the most reactive control rod stuck in the fully withdrawn position. This requirement eliminated the possibility of achieving prompt criticality through single control rod withdrawal, addressing the specific vulnerability that had made the SL-1 accident possible. Procedural requirements for reactor operations expanded dramatically following the SL-1 investigation. Maintenance procedures that had previously occupied 2 pages grew to hundreds of pages, incorporating detailed safety analysis, independent verification requirements, and explicit consideration of potential accident scenarios. The expansion of procedural documentation reflected recognition that routine maintenance operations could have safety-critical consequences that required formal analysis and control. Radiation monitoring equipment ranges were increased to accommodate emergency response activities under severe accident conditions. The failure of multiple radiation detection instruments during SL-1 emergency response had demonstrated that existing equipment was inadequate for accidents involving major radiation releases. Higher-range instruments and redundant detection systems became standard requirements for nuclear facilities to ensure that emergency responders could obtain accurate information under all accident conditions. The training requirements for reactor operators were fundamentally restructured to include detailed coverage of accident scenarios and emergency response procedures. The SL-1 operators had been well trained for normal operations but had received limited instruction in accident recognition and response. Simulator training became mandatory for reactor operators, providing opportunities to experience accident scenarios under controlled conditions without safety consequences. Organizational requirements for reactor operations were strengthened to ensure adequate technical supervision and oversight. The decision to limit combustion engineering supervision to normal working hours had reflected confidence in the reactor's inherent safety and the routine nature of maintenance operations. Following SL-1, continuous technical supervision became standard for reactor facilities, recognizing that safety-critical operations could occur during any operational period. The regulatory framework governing reactor safety was expanded to incorporate lessons learned from SL-1 forensic analysis. The Atomic Energy Commission revised reactor licensing requirements to include explicit analysis of single-failure consequences, procedural adequacy assessments, and emergency response capability evaluations. These changes reflected recognition that reactor safety could not be ensured through design analysis alone, but required comprehensive consideration of operational factors and human performance. The SL-1 accident investigation also influenced international nuclear safety standards and practices. The forensic findings were shared widely within the international nuclear community, contributing to development of safety standards that would prevent similar accidents in other reactor designs and operational contexts. The accident became a reference case for reactor safety analysis and emergency response planning throughout the world. Long-term follow-up studies provided additional insights into accident consequences and cleanup effectiveness. The SL-1 burial site, designated as EPA Superfund Operable Unit 5-5, required ongoing monitoring and eventual remediation to address persistent contamination problems. Environmental surveys conducted over decades following the accident documented the long-term behavior of fission products in the high desert environment and validated cleanup effectiveness. The 3 operators killed in the SL-1 accident were eventually buried in lead-lined caskets with special precautions to prevent radiation exposure to cemetery workers and the public. Richard McKinley was interred in Arlington National Cemetery with warnings that his remains must never be moved due to persistent radioactive contamination. These burial arrangements represented lasting consequences of the accident that would persist indefinitely. The Army nuclear power program continued following SL-1, but with fundamentally altered safety requirements and operational procedures. The Mobile Low-Power Reactor, ML-1, achieved full power operation on February 28, 1963, incorporating safety features derived from SL-1, lessons learned. However, the program was ultimately abandoned in 1965 due to financial pressures from the Vietnam War and technical problems that proved difficult to resolve within military budget constraints. The SL-1 accident established precedents for nuclear accident investigation and analysis that continue to influence reactor safety practices. The comprehensive forensic approach developed for SL-1 became the standard methodology for investigating nuclear accidents, emphasizing physical evidence analysis, experimental verification, and systematic examination of organizational and human factors. The accident demonstrated that nuclear safety required understanding not just nuclear physics, but the complex interactions between technology, procedures, training, and human performance. The fundamental lesson of the SL-1 accident was that reactor safety must be based on preventing unacceptable conditions rather than assuming they cannot occur. The accident had resulted from the failure of a basic design assumption about control rod reactivity worth, but the consequences extended far beyond simple calculational errors. The accident demonstrated that nuclear technology requires safety systems designed for actual operational conditions rather than idealized design conditions, and that human factors must be explicitly considered in safety analysis rather than assumed to be adequately controlled through training and procedures. The legacy of SL-1 persists in every aspect of modern reactor safety: design requirements that prevent single-failure catastrophes, procedural systems that provide multiple verification barriers, training programs that prepare operators for accident conditions, and emergency response capabilities that can function under severe radiological conditions. The accident that killed 3 military operators in the remote Idaho desert became the foundation for safety systems that protect nuclear workers and the public throughout the world. The reactor designed to demonstrate nuclear power's potential instead demonstrated the importance of understanding its limits.